Dear students, after studying this module, you shall be able to understand the underlying concept of nuclear magnetic resonance spectroscopy, elucidate the structural information through NMR spectroscopy, to understand the number of signals of an unknown compound obtained from its NMR spectra, to know about the spin-spin coupling or splitting, to understand the proton NMR chemical shifts for common functional groups, to know how to elucidate an unknown structure of a compound, and NMR spectroscopic applications. And we will also discuss some of the problems related to the NMR structural elucidation. Today, NMR has become a sophisticated and a powerful analytical tool that has found a variety of applications in many disciplines of scientific research, medicine and various industries. In the past 2 decades, with the development of new methodologies and instrumentation techniques, NMR has become one of the most powerful and versatile spectroscopic techniques for the analysis of biomacromolecules such as proteins, nucleic acids, etc. Together with X-ray crystallography, NMR spectroscopy is one of the 2 leading technologies for the structural determination of biomacromolecules at atomic resolution. The following are some important applications of NMR spectroscopy used by an organic chemist to elucidate structure of an unknown organic and inorganic compounds. Now let us begin with some applications of PMR, that is proton magnetic resonance, or NMR in structural elucidation of simple and complex compounds. We will first in this segment take up the identification of structural isomers. Ethanol and dimethyl ether are functional group isomers and they can be identified by proton NMR spectroscopy. In ethanol, there are 3 types of protons and hence 3 signals will be observed in the proton NMR spectra, whereas in dimethyl ether all the 6 protons are equivalent and hence only 1 signal will be observed. Now you can see how in 2 structural isomers different type of signals and different number of signals are observed. Similarly, we can distinguish through the help of NMR between N-propyl bromide and isopropyl bromide by proton NMR. The proton NMR spectrum of N-propyl bromide will show 3 signals, whereas only 2 signals will be observed in the proton NMR spectrum of isopropyl bromide. In a similar way, students, a large number of structural isomers can easily be distinguished on the basis of proton NMR spectroscopy. Now, the cases I have discussed, their structures are drawn here and you can easily see them. Detection of hydrogen bonding through NMR spectroscopy, that is the next application. In general, hydrogen bonded protons show a higher value of chemical shift than the ones which are non-hydrogen bonded. The downfield shift of the absorption depends on the strength of the hydrogen bonding. Greater is the degree of hydrogen bonding of a particular proton, greater is the downfield shift of that particular proton. The intermolecular and intramolecular hydrogen bonding can be distinguished by the use of proton NMR spectroscopy. The intermolecular hydrogen bonding depends on the concentration of the sample and decreases on dilution with a non-polar solvent and also with increasing temperature. The pure ethanol shows signals near 5 ppm, but the same ethanol, if it is diluted with non-hydrogen bonding solvents like carbon tetrachloride, CdCl3, that is deuterated chloroform, and deuterated benzene CD6, that is C6D6, the OH signal shifts upfield due to the breaking of the intermolecular hydrogen bonds. The intramolecular hydrogen bonding, however, does not depend on the concentration of the sample and hence shows no change in absorption position on dilution or with increasing temperature. Now, third application is the detection of cis-trans isomerism and conformers. Now, proton NMR spectroscopy can be easily helpful in distinguishing between cis and trans isomers because the concerned protons have different values of chemical shifts as well as coupling constants. For isomeric olefins, J trans, that is the coupling constant for trans protons, is always greater than the coupling constant for the cis protons. Thus, it is possible to determine the configuration of geometrical isomers of a disubstituted olefin easily through proton NMR spectroscopy. Similarly, students, the axial and equatorial protons can be distinguished on the basis of different values of their coupling constants and chemical shifts. The equatorial protons in a conformationally rigid cyclohexane ring appear more downfield than the axial protons on the same carbon. Now, let us move to the fourth application, that is the quantitative analysis. Proton NMR spectroscopy has been widely used to determine the relative amount of keto and enol tautomeric forms in a mixture. The structures of the keto and the enol forms. In the proton NMR spectrum of acetyl-acetone, the integration value of methylene protons was found to be 10 mm, and that for methine, that is double bond CH proton, was found to be 22 mm. The two methylene protons of keto form have an integration of 10 mm. One methine proton of the enol form has an integration of 22 mm, and hence two protons will be having an integration equal to 44 mm. Therefore, students, calculating the concentration of keto and enol forms, percentage of the keto form will be 10 divided by the whole amount, that is 44 plus 10 into 100 is equal to 18.5%, that is the concentration or the amount of keto form is 18.5% in the total mixture. However, for the enol form, we can calculate it like 44 divided by 44 plus 10 into 100, that becomes 81.5. Thus, we can easily see that the concentration of enol form is equal to 81.5%. Now, the fifth application of proton NMR spectroscopy is a use in medicine, and it is the most important use, that is in magnetic resonance imaging. The important application of proton NMR spectroscopy is magnetic resonance imaging for medical diagnosis of many diseases. Magnetic resonance imaging, that is MRI, is used to take the image of any part of the human body, especially soft tissues, in all possible planes. The brightness of various regions of an image is related to the number of protons in that particular tissue at a particular place and the relaxation time of the protons. In the body, the hydrogens of the water molecules attached to the surface of biological molecules relax faster than those present in a free liquid. Furthermore, the relaxation time of protons of water molecules is different in different types of tissues, especially in diseased tissues and non-diseased tissues. Specific pulse sequences detect these differences in relaxation times for the protons of water molecules in the tissue being examined. When the results of the scans are processed, the image produced shows different densities of signals depending upon the difference in relaxation times. Thus, the MRI image can give you an idea of the amount of abnormality present in different types of diseased tissues. Unlike other diagnostic techniques which are present right now in the market, such as computerized tomography (CT), MRI is a non-invasive and a painless technique, and it does not use any ionized radiation, and hence it is very safe. Now, coming on to the sixth application, that is the structural determination of unknown compounds. NMR spectroscopy is used to determine the structure of an unknown and novel compound, and as such is usually required by scientific journals for identity confirmation of new synthesized compounds by any chemist. As we all know that the proton spectra have three features, that is chemical shift, signal intensity and multiplicity, and each one provides an important piece of information. Here we will see how to use these particular features together to assign the structure of an unknown organic compound. Considering the first one, if the molecular formula is given, first determine the double bond equivalence of the compound, which can give important clues about the structure of the compound, whether the compound is acyclic, cyclic, saturated or unsaturated or aromatic. Zero value of dBe indicates that the compound does not have any ring or pi bonds. The dBe value of 1 indicates that the compound has either one ring or one pi bond. The dBe value of 2 indicates that the compound has either one ring or one double bond, or two double bonds or two rings. The dBe value of 3 indicates that the compound has three double bonds or two double bonds and one ring, or two rings and one double bond. The dBe value of 4 or more indicates that the compound is most likely to have an aromatic ring. Now the formula for dBe is equal to brackets 2a plus 2 in smaller brackets minus brackets b minus d, the whole divided by 2, where a is equal to number of carbon atoms, b is equal to hydrogen or monovalent atom, d is equal to nitrogen atoms. Now second rule is consider the number of signals and integration of each signal, and which gives important clues about the symmetry of the molecule. Third rule being analyze carefully the chemical shift, integration value and multiplicity of each signal, and then draw fragments relating each signal. Fourth rule is that finally attach all the fragments to get the structure of the compound. Note that there may be more than one way of joining the fragments together. Spin-spin splitting data may help you to make definite choice between two different possibilities or more than two different possibilities that you might be having. Let us begin with problem number 1. The statement of problem number 1 is an organic compound having a molecular formula C5H12O having the IR peaks at 3400 centimeter inverse. The proton NMR data done in CDCl3 is 0.95 ppm, a doublet with 6 hydrogens, 1.8 ppm, multiplet with 3 hydrogens, 2.7 ppm, a broad singlet worth 1 hydrogens, 3.9 ppm, a triplet with 2 hydrogens. Find out the structure of the given compound. Now let us discuss the solution one by one. First we have to calculate the double bond equivalence, that is according to the above formula 0. It is given here how to calculate it. dBe of the given compound is 0, that means there is no unsaturation in the given compound. IR of the given compound shows the peak at 3400 centimeter inverse, which is a stretching frequency for the OH group. The proton NMR gives 4 signals, which indicates the presence of 4 groups of non-equivalent protons. Now let us assign each of the hydrogens in each of the signals. Now first of all, a doublet at 0.95 ppm of 6 protons indicates the presence of CH3 whole twice CH group, that is dimethyl group. Remember that the multiplicity depends on the number of protons present in the neighboring carbon atom. Next, remember that the presence of a triplet at 3.9 ppm having 2 proton indicates the presence of CH2CH2O group functionality, because you can only observe a triplet if the next carbon have 2 hydrogens. Remember that a peak which is at around 3.5 to 4.3 ppm is a typical of OCH functionality as it is downfield. In addition to this, we have one oxygen atom in our molecule, and it is present in the form of a hydroxyl, which is confirmed by the IR spectrum of this compound. Now, presence of a broad singlet at 2.7 ppm is our last target. For this will account for one proton, and it is due to the hydroxyl group, which is further confirmed by the IR spectroscopy. We now have two fragments, and after assembling these fragments, the structure of the compound would be CH3 whole twice, that is dimethyl CH, CH2, CH2OH. That is, if we draw the structure, you can clearly justify the ppm values that we have assigned to each different type of non-equivalent hydrogens, and you can also justify the IR data that is given here. Now, I hope with one example you have learned how to join the dots and the fragments which is obtained from the data given in the spectral problem. Now, let us proceed towards problem number 2. An organic compound which has the molecular formula of C9H12 shows the following spectral data. In the proton spectrum, all values in ppm, we observe the first at 1.2 as a doublet with a J value of 8 Hz accounting for 6 protons, another signal at 2.87 ppm showing a septet with 1 proton, another one at 7.2 with a singlet accounting for 5 protons. Now, we have to determine the structure of the given compound. First of all, the first rule, students, is to calculate the double bond equivalence of the given unknown compound C9H12. Calculating the DBE from the formula, as I have stated before, the DBE comes out to be 4. Now, as I have already stated that if the DBE is 4 or more, then the given compound may be aromatic. The proton NMR signals gives 3 signals, which indicates the presence of 3 sets of non-equivalent protons. Let us see first of all a doublet which occurs at 1.2 ppm accounting for 6 protons, and it indicates the presence of again a dimethyl group attached to a CH. This also confirms the presence of a septet of 1 proton at 2.87 ppm. Now, you can see the structure of the fragment that we have elucidated from this particular information. Now, presence of a singlet of 5 protons at 7.2 ppm definitely indicates a presence of a mono-substituted aromatic ring, as we have also come to know from the DBE, which is equal to 4. Now, based on the fragments obtained from the information given in the problem, the final structure would be this substituted aromatic ring, which is mono-substituted with a isopropyl group. This is the final structure of the compound. Let us now move to another problem, problem number 3. Molecular formula of an organic compound is C7H12O3, which exhibits the proton NMR and IR data as follows. The IR data is 1710 centimeter inverse, 1750 centimeter inverse. They have given only 2 peaks to you, students. And coming on to the proton data, all the values in ppm. First one is 1.25, which occurs as a triplet accounting for 3 hydrogens. Another one at 2.2 ppm with a singlet accounting for 3 hydrogens. Another signal at 2.55 ppm accounting for a triplet with 2 hydrogens. Another signal at 2.7 ppm with a triplet at 2 hydrogens. The last signal is 4.15 ppm with a quartet accounting for 2 hydrogens. Now, we have to determine the structure of the given compound. For the solution of this problem, if you take a look at the formula of the given unknown compound, it is C7H12O3. In this, the double bond equivalence as calculated by the formula will come out to be 2. Thus, the DBE of any given compound is 2. That means there is an unsaturation in that compound. However, the proton NMR data does not show any peak in the region of 4.5 to 6.8 ppm, which is characteristic of any unknown compound having unsaturation in it. Analyzing the IR data of the given compound, it shows 2 peaks, one at 1710 centimeter inverse and the other one at 1750 centimeter inverse, which indicates the presence of a carbonyl group. The peak at lower frequency, that is at 1710 centimeter inverse, is characteristic of the keto group, whereas the peak at 1750 centimeter inverse is due to the ester functionality in any given unknown compound. Now let us come back to the proton signals. The proton NMR gives 5 signals which indicates the presence of 5 sets of non-equivalent protons. A doublet at 1.25 ppm of 3 protons indicates the presence of a CH3-CH2 group. Next, a singlet at 2.2 ppm of 3 protons indicates the presence of CH3CO group, that is the carbonyl group, especially the keto group. Now remember that the CH3 protons in CH3COCH3, that is acetone, resonates at 2.15 ppm. Coming to the next set of given information, a quartet at 4.15 ppm of 2 protons indicates the presence of 1OCH2CH3 group. Remember that the peak around 3.5 to 4.3 ppm is typical of the OCH functionality. Now let us move to the last set of information that we are having with ourselves. 2 triplets at 2.55 ppm and 2.7 ppm, each accounting for 2 protons. This indicates the presence of CH2-CH2 group. Since the methylene protons show coupling due to each other only and with no other protons, this indicates that both the methylene carbons are attached to the CO functionality. Now let us join all the fragments of information that we have elucidated from the given set of values of proton NMR and the IR. The structure of the given compound would be CH3CO, CH2CH2, COO, CH2CH3. Now you can see from the structure of the compound that is drawn here, we can easily see and account for each ppm value given in the proton NMR as well as each of the IR values which are given in the problem. Now see how easily we can determine the structure of an unknown compound by actually joining all the fragments from the data that we have obtained and from the fragments we have obtained from the data given to us. Now students, let us discuss a very interesting aspect of NMR spectroscopy, that is two-dimensional NMR spectroscopy. Since the development of pulsed NMR spectroscopy, a number of advanced two-dimensional NMR techniques have been devised. There are various types of 2D NMR experiments such as correlation spectroscopy, short form COSY, heteronuclear correlation spectroscopy, short form HETCOR, exclusive correlation spectroscopy, short form ECOSY, total correlation spectroscopy, short form TOCSY, incredible natural abundance double quantum transfer experiment, short form inadequate, heteronuclear single quantum correlation spectroscopy, HSQC is the short form, heteronuclear multiple bond correlation spectroscopy, short form HMBC, nuclear Overhauser effect spectroscopy, short form NOESY, rotating frame Overhauser effect spectroscopy, that is ROESY, ROESY. They are especially valuable techniques when the structure of a complicated natural products is to be considered and the conformation of biomolecules has to be determined. Out of these several experiments, two find the most frequent applications to NMR organic chemists. These two are proton-proton correlation spectroscopy, abbreviated as COSY, correlated spectroscopy that is, and 13C proton correlation spectroscopy, that is heteronuclear correlation, also known as HETCOR. In one-dimensional proton NMR, there are two axes. One represents the chemical shift and the other intensity of the signal, whereas in 2D NMR spectroscopy, there are three axes. Out of these, two axes represents the chemical shift and the third one represents the intensity of the signal. In COSY experiments, both the axes have chemical shifts of the protons, whereas in HETCOR the chemical shift range of the proton is plotted on one axis and the chemical shift range of the 13C is plotted on the second one. Thus, COSY identifies pairs of protons which are coupled to each other. HETCOR on the other hand is used to identify carbon atoms and protons directly attached to it. Now let us now discuss in detail COSY. To see what type of information we can get from a COSY spectrum, let us consider the COSY spectrum of 2-hexanone, which is a carbonyl compound, a keto compound. Both the x and y axes have one-dimensional proton NMR of 2-hexanone. Each axis is calibrated according to the chemical shift values in ppm. Now you can see given here are the ppm values of 2-hexanone of the proton spectra. You can observe that there are many contours lying along the diagonal extending from the lower left corner to the upper right corner. This diagonal bisects the 2D NMR into two parts which are mirror images of each other. The off-diagonal contours are also called cross peaks and contain the connectivity information that we require. The contours lying on the diagonal serve only as reference points. Now each cross peak has x and y coordinates. One coordinate corresponds to the chemical shift of a proton, the other to the chemical shift of a proton which to it is coupled. Because that diagonal splits the COSY spectrum into half, each cross peak is duplicated on one other side of the other diagonal with the same coordinates except in reverse order. Therefore, we only need to examine only one half of the cross peaks. Now to examine the COSY, we just start with a cross peak and draw two perpendicular lines, that is dashed lines, connecting to the diagonal. These lines are parallel to each spectrum axis. The peaks which are intersected on the diagonal by these lines are said to be coupled to one another. Now you can see what I have said in this particular figure and it is clearly visible and understandable. Now let us start by analyzing the COSY spectrum of 2-hexanone. First, consider the off-diagonal spot at 1.6. Now draw a horizontal line from this point. This line intersects the spot on the diagonal that corresponds to the H2 proton. Again, draw a vertical line from the same off-diagonal spot. This line intersects the spot on the diagonal corresponding to the H3 proton. Now this relation shows that the H2 proton is coupled with the H3 proton. Similarly, draw another horizontal and a vertical line from the off-diagonal spot at 1.3. These two lines intersect the spots on the diagonal corresponding to H3 and H4 protons respectively. This confirms that the H3 proton is coupled with the H4 proton. Similarly, we can show the coupling between H4 and H5 protons. Now it is important, students, to note here that the diagonal peak at 2.1 due to H1 proton has no cross peaks on the other side, which shows that H1 proton is not coupled to any other proton in the molecule. Now I hope from this correlation spectroscopy you can understand the influence of coupling and you can understand the importance of coupling in a particular molecule. Now let us consider HETCOR in detail. HETCOR, as I have already told you, stands for heteronuclear chemical shift correlation, and it is also a type of COSY experiment in which two axes belong to the same chemical shifts but for different nuclei. That is, one axis stands for the proton and the other for the carbon 13. By HETCOR spectrum, we can determine that which hydrogen is attached to which carbon. There are no diagonal peaks in HETCOR and it is composed of only cross peaks, each relating to a carbon to its directly attached proton. Now let us look at the HETCOR spectrum of 2-hexanone again. In these we can see the difference between the COSY and the HETCOR of the same compound. to explain the correlation between proton and carbon atoms. Now 13C NMR spectrum is shown on the x axis and the NMR, that is the proton NMR, is shown on the y axis. Now you can see here in this figure that the proton and the 13C values are given. Interpreting the spectra is pretty straightforward. If you draw a vertical line and a horizontal line from a spot designated as A, it indicates that the hydrogens that show a signal at 0.9 ppm in the proton NMR are bonded to the carbon that shows a signal at 14 ppm in the carbon 13 NMR spectrum. Similarly, a cross peak at B shows that the hydrogens that show a signal at 1.3 ppm are bonded to the carbon that shows a signal at 22 ppm. In a similar manner, you can identify the attachment pattern for other carbons and hydrogens easily. If a line does not have any cross peak, this means that the carbon atoms are not directly attached to any proton, for example a quaternary carbon. Here the chemical shift of the carbonyl is not displayed in this 13C spectrum because it has no attached hydrogens. Now an important point to note here is that although the one-dimensional proton and 13C spectra of 2-hexanone are simple enough to be interpreted directly, however, these techniques are more frequently used in case of many complicated molecules where signals can be only assigned with the help of 2D NMR spectroscopy. Now students, let us summarize this module. In the past 2 decades, NMR, being a sophisticated and a powerful analytical tool, has become one of the most powerful and versatile spectroscopic techniques for the analysis of biomacromolecules such as protein, nucleic acids. Now NMR is extremely useful in the detection of functional isomers, hydrogen bonding, cis-trans isomerism and conformers. Proton NMR spectroscopy has also been used to determine the relative amount of keto and enol in the tautomeric mixture. Magnetic resonance imaging (MRI) is one of the most powerful tools in modern clinical diagnosis, which is based on the topological representation of NMR parameters like proton density and transverse relaxation times and longitudinal relaxation times. Now differences in these parameters allow impressive anatomical discrimination to be made, and it makes it possible to distinguish pathological tissues from healthy tissues. Now NMR spectroscopy is also used to determine the structure of unknown and novel compounds and also known and novel compounds, and as such it is required by scientific journals for identity confirmation of newly synthesized compounds. Two-dimensional nuclear magnetic spectroscopy is a set of nuclear magnetic resonance spectroscopic techniques in which the data plotted in space is defined by 2 frequency axes rather than 1. Many 2D NMR techniques are there like HETCOR, COSY, eCOSY, NOESY, HMBC, HMQC, ROESY, HSQC, inadequate, TOXY, etc. These techniques are very useful for detection of various structural aspects of an unknown compound. COSY and HETCOR have been described in this module in detail. I hope students, you have found this module very informative.